The position vector. Welcome, everyone. Today, we are beginning a new and very important topic in our study of vector algebra. Now, before we can start calculating or moving vectors around, we need a starting point. Think about it. If I told you to meet me at a specific location, you wouldn't be able to find me unless we both agreed on a fixed reference point, a home base of sorts, from which we can measure distance and direction. In mathematics, to describe exactly where any point in space is located, we must have this fixed reference point. This brings us to the core of today's lesson, the concept of the position vector, which is the fundamental tool we use to anchor our points to that reference point. Understanding the concept. Now that we've established why we need a fixed reference point, let's dive into how we actually set that up. To describe where a point is located in a three-dimensional space, we use what is known as a right-handed rectangular coordinate system. Think of this as a framework of three axes that are all mutually perpendicular, meaning they meet at right angles to one another. We call these the x-axis, the y-axis, and the z-axis. The very heart of this system is the point where all three of these axes intersect. We call this point the origin, and we denote it with the capital letter O, which has the coordinates 0, 0, 0. This brings us to our main topic, the position vector. A position vector is simply a vector that represents the location of any point specifically in relation to this origin. So if we have a point, let's call it point P, with coordinates x, y, and z. The position vector of P is the directed line segment that starts exactly at the origin O and ends at point P in the next slide. We will look at the specific mathematical notation we use to write this down. Notation and representation. Now that we understand what a position vector actually represents, that directed line segment from the origin to a point, let's talk about how we write this down in our notebooks. There are a few different ways you'll see this written in your textbooks and exams. First, we can denote the position vector of point P as vector OP. Using this notation is very helpful because it explicitly shows you the direction of the vector. It tells you clearly that the vector starts at the origin, O, and ends at our point, P. However, you will often see a much simpler notation, just a lowercase r with a vector arrow on top. We use this general notation, vector r, when the origin is already implied, so we don't need to write out the O every single time. Now, what happens if we are dealing with a whole set of different points? Let's say we have points A, B, and C to keep our work organized and easy to read. Mathematicians follow a standard convention. Instead of writing out vector OA or vector OB every time, we simply use lowercase letters. So, the position vector for point A is written as vector A, for B as vector B, and for C, it is vector C. This shorthand is going to be incredibly useful in the next few slides, especially when we start calculating the magnitude and distances between these vectors. Magnitude of the position vector. Now that we know how to represent a point using a position vector, let's talk about how we measure it. Specifically, we want to find the magnitude or the length of that vector. Think of the magnitude as the straight line distance between our starting point, the origin, which we've labeled O with coordinates 0, 0, 0, and our destination point, P, with coordinates x, y, and z. To calculate this, we use the distance formula, just like you would in three-dimensional space. If we look at the vector op, the magnitude is equal to the square root of the quantity x minus 0 squared plus y minus 0 squared plus z minus 0 squared. But as you can see, since subtracting 0 doesn't change the value, we can simplify this significantly. The formula simplifies to the square root of x squared plus y squared plus z squared. And just a quick reminder of our notation from the previous slides. You will often see this magnitude written simply as the magnitude of r, which is written as the absolute value of r. This value tells us exactly how far the point is from the origin, a concept we are going to apply practically in our next slide involving drone navigation. Real-world example, drone navigation. Now that we have covered the theoretical notation and the formula for magnitude, let's put everything we've learned into a practical context. Imagine a drone taking off from a launch pad. To make our calculations easy, we will treat this launch pad as our fixed reference point, or the origin, which we denote as O, with coordinates 0, 0, 0. As the drone flies away, it reaches a specific point in the air, which we'll call point P. According to its flight logs, the drone's position is recorded as 3 meters east along the x-axis, 4 meters north along the y-axis, and 12 meters high along the z-axis. Let's walk through the step-by-step calculation to find the position vector and its magnitude. Step 1. First, we identify the coordinates of our point. Based on the flight data, the coordinates of point P are 3, 4, 12. Step 2. Next, we express this as a position vector. Using the notation we discussed in the previous slide, the position vector of the drone, which we can call OP or simply R, represents the directed line segment from the launch pad to the drone. Step 3. Now, we apply the magnitude formula to find the direct, straight-line distance from the launch pad to the drone. We use the formula where the magnitude of R equals the square root of x squared plus y squared plus z squared. Step 4. Let's substitute our specific values into that formula. We have the square root of 3 squared plus 4 squared plus 12 squared. When we calculate those squares, we get the square root of 9 plus 16 plus 144. Adding those together, we get the square root of 169. Step 5. Finally, we find our result. The square root of 169 is 13. So the magnitude of our vector is 13 meters. This tells us that the drone is exactly 13 meters away from the origin. As we move to the next slide, keep this calculation in mind, as I will highlight some common pitfalls students often encounter when working with these types of problems. Common mistakes to avoid. First, please be careful not to confuse a point with a vector. This is a subtle but vital distinction. A point, let's call it P with coordinates x, y, and z, is simply a fixed location in space. It's a destination. However, the position vector, which we denote as r, is not just the destination. It is the directed line segment that starts at the origin and travels to that location. While they are closely linked, remember that one is a location and the other is a movement or a displacement. Second, never ignore the importance of the origin. As we discussed in our earlier slides, a position vector is always relative to a reference point. If a problem doesn't explicitly state a different reference point, you must always assume that your starting point is the origin, O, with coordinates 0, 0, 0. Without this fixed starting point, the vector loses its meaning. Finally, watch out for sign errors when calculating the magnitude. When you are finding the magnitude of r, you are squaring the x, y, and z components. It is a common mistake to let a negative sign slip through, but remember that any number, whether positive or negative, becomes non-negative when squared. For example, if your x-coordinate is -3, when you calculate x squared, it becomes +9. Always ensure your squared terms are positive before you sum them up and take the square root. Now, before we wrap up our lesson, I want to pause and discuss some common pitfalls. Even if you understand the formulas, it is very easy to make conceptual or calculation errors in vector algebra. Let's look at 3 specific mistakes to watch out for. Keep these tips in mind, and you will find that working with position vectors becomes much more intuitive. Now, let's move to our final slide to summarize everything we have learned today. Key takeaways. First, remember that the position vector, which we denote as r, is essentially the bridge that connects our fixed reference point, the origin O with coordinates 0, 0, 0, to any specific point P with coordinates x, y, and z. Second, keep your notation consistent. You can write this vector as op, which explicitly shows the path from the origin to the point, or simply use the shorthand r. Third, don't forget how to calculate the magnitude. The magnitude, or the length of that vector, is simply the straight line distance from the origin to the point. We calculate this by taking the square root of x squared plus y squared plus z squared. Finally, just a quick reminder on mathematical convention. When we are dealing with multiple points like A, B, and C, We represent their respective position vectors using lowercase letters, specifically a vector B, and vector C. All right, we have reached the end of our lesson, so let's take a moment to recap the key takeaways to ensure everything is clear before we move on to more complex vector operations. If you have mastered these fundamentals, you are now well prepared to tackle vector addition and subtraction in our next session. Great job today!